Hello, and welcome to my ICR talk on bursting bubble in a viscoplastic medium. I'm Vatsal Sanjay, and I'm from Physics of Fluid Group in the University of Twente. This work has been done in collaboration with Maziar Jalal, who is in University of Cambridge, and my PhD supervisor, Detlef Lose. Before we begin, let me tell you what the process of bursting bubble is. Once a gas bubble is formed in the liquid bulk and it approaches the liquid gas interface, it deforms it, leading to a formation of this thin liquid layer. As this liquid layer drains and ruptures, it creates some film droplets. And as you can see, now there is a very high surface energy cavity which has been formed. And this cavity will collapse because of surface tension. In fact, the rim connecting this cavity to the free interface will retract, which will initiate the flow. So whenever I say the bursting bubble, what I mean is this fourth stage of the process, which is collapse of this bubble cavity. Now this process is very common in nature. And the most common example would be a bursting bubble in a glass of champagne. So what happens below the champagne air interface is that as the film retracts, it creates a train of capillary waves which focus at the bottom and lead to the formation of a Waddington jet over the interface, which can result in formation of droplets as it breaks. So this is a surface tension driven flow. And what we want to study is this flow in presence of a yield stress fluid. These are the fluids which flow only when the stress applied is higher than a critical value. And for this study, we will do direct numerical simulations using a free software program called Basilisk C, which was developed by Stéphane Popinay in France. In this method, we use the volume of fluid technique to track the interface and solve for the continuity equation in both gas as well as liquid. Furthermore, we solve the Navier-Stokes equation with all its terms. So all the equations here are in the dimensionless form, and these have been non-dimensionalized using the inertial capillary velocity in time scales. And the reason is that this process is dominated by the capillary forces. Now you can see a bond number in the Navier-Stokes equation, and this bond number is the ratio between the gravity forces and the surface tension forces. And this bond number determines the shape of this cavity at t is equal to 0. For simplicity, we are going to assume that this bond number is very close to 0, which means that the initial shape would be simply a sphere connected to a flat free interface. Now, it is very important to take care of this viscous stress term if we want to model a non-Newtonian liquid. And for that, we use a regularized Bingham model. In this model, the flow is 0 if the stress is below a critical value. And if the stress is higher than a critical value, then the constitutive equation looks like this. And in these equations, we can identify two dimensionless number. First is the Ohnesorg number, which is nothing but a ratio between the viscous stresses and the surface tension stresses. The second number is a J number, which is a ratio between the yield stress of the fluid and the capillary stress. So in this phase map, if J goes to 0, then we are in the Newtonian limit. So let us first start by looking at Ohnesorg number of 10 to the power minus 2, which is the case of a Newtonian liquid. In this video, the left-hand side shows the magnitude of the velocity vector and the right-hand side shows log 10 of the deformation tensor. The observations in this video are very similar to what we saw in the experiment before. Flow starts as the rim retracts, and then it results in the formation of a train of capillary waves which focus at the bottom of the cavity and resulting in the formation of a Waddington jet, which also forms droplets because of the Rayleigh plateau instability. Now we can further characterize this jet by following the interface at the center line, which is over here. So in this video, we see as the waves focus at the bottom of the cavity, there's a very high acceleration, which is followed by formation of droplets. These which corresponds to these kinks in the graph, and ultimately the interface settles down to a flat free surface configuration. Now, those were the Newtonian liquid cases, which has been widely studied. Now let us look at a viscoplastic case. In this case, we have a J value of 0.1, which is finite but very small. And in this particular case, the right-hand side has a spatial meaning, which is that if the value is very small, so if the region is black, then it denotes a plastic region. On the outside, the process is very similar to its Newtonian counterpart in terms of formation of waves and the formation of the Waddington jet. However, they are very distinct wavy yield surfaces which are formed in this particular case. And we can compare this with the Newtonian case over here. And we see that the jet which was formed in case of a viscoplastic liquid is weaker and less and shorter than the Newtonian liquid. Furthermore, we also see that there are fewer droplets which are formed in case of a viscoplastic liquid as compared to the Newtonian liquid. In fact, as we increase the J number, the jet becomes even weaker and the number of droplets are decreased even further. And this happens because there is an increase in the effective viscosity because of an increase in the J number. Even though there are some distinct differences in these cases, one thing which is common in all these cases is that they still lead to the formation of this droplet, which forms the first regime in our simulations, which happens at J numbers which are very small and Onizog numbers which are also small, where we form this Waddington jet leading to the formation of droplets. Now let's see what happens if we go beyond this region to a case where the J number is higher, which is the J of 0.25 and Onizog of 10 power minus 2, which is the case over here. And here we see that the jet still forms, but the flow is too weak to create any droplet and there is no pinch off. Also, we notice this wavy yield surface that is also characteristic of these kind of flows with capillary waves. So this is the regime where there is no pinch off, but there is still a jet which forms and crosses the z=0 line. Now let us see what happens if we go further beyond this region. This is a case with J number of 0.3. And now we see that the flow is so weak that the central line interface never crosses the h=0 line. However, there is still a very distinct acceleration caused due to the focusing of capillary waves. But the flow is way too weak for the jet to be formed in these cases. So this is the third regime that we find. If we keep on increasing the J number in such a way, then we see that the reason of this strong acceleration keeps on decreasing until we reach a very such high values of J that the central line interface never leaves its initial position, which is one such example is shown in this video. So we see that there is always a part of the cavity which never yields. And this leads to the formation of the fourth reason in our phase map, which is over here. Now, we know that capillary waves are very important in the process of bursting bubble. So in this part of the talk, we are going to focus on the effect of yield stress on the capillary waves. And for that, we track this capillary wave as it travels down the interface by looking at the angular location theta c. And for a Newtonian liquid, this capillary wave travels down with a constant angular velocity. And this angular velocity is independent of the Onizog number, as long as the liquid is Newtonian. Now, once we introduce viscoplasticity in the medium, we see that for initial time, the capillary waves still follow the trajectory which is common to its Newtonian counterpart, However, after some distinct time, there are apparent deviations from this Newtonian trajectory. And we see that as we increase the J number, this deviation is more pronounced. In fact, if we go to a very high J number case, we see that there is a quite obvious competition between the capillary wave, which is trying to yield this interface, and the viscoplasticity, which is opposing the flow. And this for this example is shown for the case of J of 1. And as we further increase the J, we see that this deviation from the Newtonian behavior happens earlier, and also that the final location of the frozen capillary wave is closer to the initial position. So much so that for very high J numbers, the flow only happens in the initial rim, which retracts at the boundary of the cavity and the free surface, and this wave freezes at a constant location. And as you can see for this case over here, and for different other cases before, in presence of a yield stress liquid, the flow stops once the stress are below the critical yield stress value, and this can lead to some final crater shapes which has a non-zero surface energy. And we can characterize these final crater shapes using the same Onizorg and J phase space that we used before. And we see that for the first regime, we have these jets which relax back and form this shallow crater with non-zero surface energy. Furthermore, in the second regime, where there are no droplets, but still a jet forms, and this jet relaxes back to form this shallow craters. However, as the J increases and the jet no longer crosses the free interface, it freezes before it could it can reach the h equal to 0 line, leading to these characteristic shapes, which are deeper than the low J value cases, but they are still shallow. Ultimately, we reach to the very high J number cases where the plasticity of the medium doesn't allow the entire cavity to yield, leading to the final shapes which are very close to the initial condition. With this, I come to the highlights of this talk. So we have done a phenomenological study of bursting bubble in a viscoplastic medium, and we see how viscoplasticity affects the overall flow dynamics. Furthermore, we focused on the capillary waves and how it behaves in the presence of a yield stress liquid, and we saw that for initial time, the waves still behave similar to their Newtonian counterpart, but for late times, there's a strong dependence on the yield stress liquids. And lastly, we use the capillary Bingham number and the Onizorg number to characterize different features of the flow that we see. Now, I would like to thank my collaborators for their help in this project. And with that, I would also like to end my talk. And if you have any questions, I would be happy to take them now, or you can send an email with my email ID is over here. And lastly, Basilisk C is a free software program, and in that spirit, all the codes that are used in this talk are available on the website, which is given over here. Thank you for your attention.